Try this topic, Unit 10, Properties of Matter. Unit 10, Properties of Matter. Unit 10, Properties of Matter. So this is the 10th unit. If you have any problems at that moment, send me a message. Okay. Unit 10, Properties of Matter. Right. So this unit contains 3 parts. First one is elasticity. Then viscosity. Other one is surface tension. So this unit contains can be divided into 3 main parts. So the first part we are going to talk about is elasticity, which includes I think everyone has downloaded the tute, those who didn't get the tute from the mail. Right. So the first part is elasticity. Just take all this on the notebook, right? The questions will be done on the separate papers or something like that. Okay, Unit 10, Properties of Matter. Under that, right, elasticity. Elasticity. Right. First, I'll just give you a note. As you're writing the note, you have to understand. I'll explain that later. First, you have to take the note, right? Okay. Write down by applying an external force on a solid substance. Force on a solid substance. Its shape can be changed on a solid substance. Its shape can be changed. Changed within brackets, right? Deformed. Within brackets, right? Deformed. Then from a new line, right? When a force is applied on some substances, when a force is applied on some substances, its shape changes. Its shape changes. And when the force is removed, it regains its original shape. It regains its original shape. It regains its original shape. Such substances are called elastic materials. Elastic materials. Underline elastic materials. underlying elastic materials. So examples, write down examples: metal, rubber. These are simple theory parts, so I'm not going to explain too much. Such substances are called elastic materials, underlying elastic materials. Then write examples: metal, comma, rubber. Metal, comma, rubber. Then from a new line starts. From a new line start the sentence. This property which contains in solids and sometimes liquids and gases is called elasticity. It's called elasticity. Underline elasticity. Right. Then write from a new rule. Some solid materials, comma, when a force is applied, its shape changes, and when the force is removed, it does not take its initial shape. Such materials are called plastic materials. So example for a plastic material is just clay, right? Clay. So if you like compress like a lump of clay, it doesn't regain its original shape. Right? It just changes its shape. So earlier, when we talk about objects, when we apply Newton laws, when we talk about objects, we were like applying F equals ma, but we didn't think about the deformation of those objects due to that force, due to applying forces. So those are called those are rigid objects, right? But in this lesson, we are talking about the deformation of objects due to forces that are applied, right? So that is all we talk about in elasticity, right? I think everyone got the notes. right? So basically what the note says is there are two types of materials. I think everyone understands that. Two types of materials. One type is elastic materials. One type is elastic. Other type is plastic. So elastic materials, when you give a force to that elastic material and when you remove the force, that material regains its original shape, just like rubber, right? Rubber, and this property is included in metals as well, though it is not that visible. Rubber and metal, they regain its original shape once you remove the force. So those are called elastic materials. Other type of materials is plastic materials. So plastic materials does not regain, even when you remove the force, the plastic materials do not regain its original shape. Just remember elastic materials and plastic materials, right? Right. So these are like usually stuff, right? Okay. Then write the topic Young's modulus. Write the topic Young's modulus. Like this, Young's, this is a scientist, Young modulus. Within brackets, capital Y. Within brackets, capital Y. Right. Take a note. Write down. When a tensile force, when a tensile force when a tensile force is applied on when a tensile force is applied on a material shaped into a wire or a rod, it causes an extension. It causes an extension. Within brackets, simple E. In front of extension, write simple E. Okay. I'll read that again. When a tensile force within brackets capital F, when a tensile force within brackets capital F is applied on a material shaped into a wire or a rod, it causes an extension within brackets simple E. I think you understand that, right? Like, let's say the material is like iron, right? Iron. So you have to shape it into a rod, or this could be a string. So what you are applying is a tensile force. Tensile force is you are pulling this one. That's how you apply tensile forces. So what happens when you pull this one here? This extent, then that extension we call that simple E. Then the applied force is capital F. Let's say this has a uniform cross section, and that cross section is capital A. Cross section is capital A. you apply this. This is a tensile force. This is not a compressive force. This is a tensile force because you are pulling this one here. Because you are pulling this, this is called a tensile force. And you make an extension. You made an extension. So that what that sentence means. Okay, below that sentence, draw this one. Draw this one below that sentence. And this has a capital L length as well, right? This is the initial length. Mention that as well. Capital L. This is the initial length. Quickly draw that. If you draw that, send me a thumbs up or something, right? If you drew that, send me a sound or send me a message. This has a uniform cross section. Okay, send me a message. Okay. Then on the another line, write this. When a compressive force, write down, when a compressive force, capital F, when a compressive force, capital F, is applied on a material shaped into a rod, it causes a compression. Within brackets, simple e, within brackets, simple e, right? So this is what happens. So this is tensile force, right? Then another one, you are applying a compressive force. You are not applying compressive forces on strings, but that's why this should be a rod. This is the rod. It has a capital L length and the cross section, uniform cross section, capital A. And when you apply a force like this, it compresses. Let's say this much. And that compression, we call that simple E. Compression, we call that simple E. Right. Below that sentence, right, draw this one, right? Only this one. So this is for compression. Compressive force causes a compression. Draw this one below that sentence. Send me a message, right? Once you draw that. Okay, once you drew that, send me a message. So this is tensile force and this is compressive force. Right. So clearly understand these terms, right? Clearly understand these are not like complicated, but you have to clearly understand these. Right. Then write below the whole thing, right? Write down force applied on a unit area. Force applied on a unit area. Force applied on a unit area is called uh, stress. Stress. Symbol of that sigma, right? This is like pressure as well, but in this unit we are talking about we call that stress. So this is the force applied on a unit area, so we call that stress. Okay, then below that, right? So according to the definition, stress is what? Force divided by area. Force divided by area. Force divided by area is the stress. In this unit, we call this stress, not pressure, right? Then in front of this, you can write dimensions. So you have to find dimensions of stress. Dimensions. In front of this. So force is mlt minus 2 mass acceleration divided by cross section, that is L squared. So when you simplify that, ml minus 1 t minus 2, this is the dimensions of stress. Take it down. Dimensions of stress. Then fundamental units. We'll write fundamental units. Fundamental units of stress. So you can write fundamental units based on the dimensions, right? So capital M, that is kilogram. L minus 1, that is per meter. And T minus 2, that is per square second. Write that, fundamental units. So remember those terms, right? This is fundamental units based on dimensions. Then derivative units. Derivative units. So you know derivative units, this should have the units of pressure, right? Same thing. So Newton is a derivative unit. Newton per square meter when you divide that by area. And also we can write Pascal as well to find the stress. Draw a margin around this. Stress is equal to force divided by area. If you have any problems, send me a message. I think all of you have written this. Right, so we learned about stress. Then write a sentence. This is like a point. Fractional change of length, fractional change of length is called strain. Underline strain. Fractional change of length is called strain. Underline strain. So we talked about stress. This is strain, right? Strain. Within brackets, this is the symbol of strain. Epsilon. Strain. Okay. For strain, this is the equation for strain. Strain is equal to, so that is the extension, fractional change of length. Extension divided by the initial length. So E divided by L. So this is strain. Write that down. Strain is equal to E divided by capital L. Strain is E divided by capital L. So we call that fractional change of length, right? So you write that as you write that as so that is epsilon, right? That is epsilon. Okay, then we will think about units. So what should be the, units and dimensions of strain? Actually, this doesn't have units, right? A length is divided by a length, so it doesn't have dimensions of units. Under this, write down strain does not have units or dimensions. Strain does not have units or dimensions. Right? Okay, so these two are like the main two things, stress and strain. So stress is force divided by area. Area means cross-sectional area. And strain is extension divided by original length. Capital L is original length. We still didn't talk about Young's modulus. First, stress and strain should be clearly defined, right? Then write under that, write up to a certain limit, up to a certain limit, up to a certain limit, put a comma, up to a certain limit, put a comma, this one, force over area is proportional to E over L. So stress is proportional to strain, right? Stress is proportional to strain. Write this down, write this down. Stress is proportional to strain. So when you see this, you should remember an equation, right? Equation for force constant, this equation, F is proportional to E. So meaning F is equal to KE. But in this part, that equation is a bit advanced, right? Here the equation is a bit advanced because we are talking about deformations. Right, so stress is proportional to strain. So you know that whenever there's a proportionality, you can put, whenever there's a proportionality, you can put a constant and make it an equation. Make it an equation when you put a constant. So I'm going to put a constant y E over L. Okay, here now you get Young's modulus. So that constant is the Young's modulus, right? So this is the main equation. This is the main equation that you have to deal with, right? Stress is equal to y E over L. Take it down and draw margin. Take it down, draw margin. If you're okay, send me some thumbs up, right? Right. I think you have written all of these. Okay, then write under that, right here, capital Y is the Young's modulus. Capital Y is the Young's modulus. Here capital Y is the Young's modulus. Young's modulus of materials. Young's modulus of materials that make up, Young's modulus of materials that make up rod or wire, that make up rod slash wire, rod slash wire. It is, next sentence, it is, at the same line, right? It is a constant for the material. It is a constant for the material. It is a constant for the material. Right. It is a constant for the material. Right. So this is the main equation, right? But we will be using a different forms of the same equation, right? Under this one, right? Sorry, under those sentences, right? y equals, I can take this whole thing to this side, right? You can cross multiply this whole thing to this side. Then you can write f over a divided by e over l. So when we are doing questions, you will see. So this is one of the form that we are going to use. Young's modulus, another way to write Young's modulus is stress divided by strain. Okay. So you just have to remember one equation, right? You don't have to remember all the forms. Then you can derive this. Just write this one. Just write this down. Below this equation, write this sentence. So capital Y is the stress. Capital Y is the stress required to cause a unit strain. Stress required to cause a unit strain. Right. Okay, then I'm going to talk about dimensions and units of Young's modulus. Under that, you can write this. So what is the dimension? This doesn't have dimensions. This is the strain, length divided by length. So this doesn't have a dimension, right? Force divided by area. So that should have these dimensions. Force mlt minus 2 divided by area, L squared. So dimension should be ml minus 1 t minus 2. So this also has the same dimensions as stress. Remember? Because this doesn't have dimensions, right? You have to divide this by 1. Doesn't make a difference. So the dimensions of Young's modulus is ml minus 1 t minus 2. Just take it down. Then fundamental units. So what is a fundamental unit? Based on dimensions, fundamental units are based on dimensions. Kilogram per meter per square second. Take it down. Then derivative units. Derivative units should be same, right? Newtons per square meter or Pascal. Because this doesn't have dimensions. This doesn't have dimensions. If you have any problem, please send a message. Send a message, right? If you have any problem. Okay. So now we know what stress is and strain is and Young's modulus. Those are the three key terms, right? Stress, strain, and Young's modulus. Then write, below that write, example. Why? So this Young's modulus only depends on the material, right? Steel. So this is Young's modulus of steel. Young's modulus of steel. You don't have to remember these values, right? I'm giving you this just as examples. Take this down. 2 times 10 to the power 11 newtons per square meter. Young's modulus of steel. Then Young's modulus of copper. 1.2 10 to the power 11 newtons per square meter. So these are large values, right? It is defined for the material, right? It only depends on the material. Take this down. Then Young's modulus of brass. You know brass, right? So that value is, take it down, 10 to the power 10 newtons per square meter. 10 to the power 10 newtons per square meter. So these are just examples. Right. I'll just write the previous equation. Okay. So then from this equation, I can cross multiply this L to this side, Y to this side. Don't write this. Just listen first. So this is the initial form of the equation. So I'm going to subject simple E. So if you subject simple E, what do you get? FL divided by YA. So this is simple E, right? Simple E is FL divided by simple E. Sorry, FL divided by YA. Write only this equation. Write only this equation. FL divided by YA. You don't have, you know that this is derived from the same equation, right? I just subject E here. Write this one. Okay, under that write when capital L, capital A, capital F, when capital L, A and F are constant, comma, then write below that, write if Y is high, like this, write it like this, if Y is high, E is less. If Y is high, E is less. Then if Y is less, E is high. If Y is less, E is high. Write that down. If I'm going to quickly, just send me a message, right? If you don't understand something. Okay, just write this. These points you will need when we are doing questions. That's why I'm giving you this, right? Okay, how does this happen? When these are constants, L, A and F. So you are applying the same force on a rod. same rod, if you compare the two rods and if you apply same force, but the rods are made of different materials. Rods are made of different materials, meaning only Y changes. Only Y is the variable when you are comparing two rods. Let's say one rod is brass, other rod is copper. One rod is brass, other rod is copper. So since this has inversely proportional to the Young's modulus, is inversely proportional to the Young's modulus when Y is higher, E is lower, right? So here if you have two identical rods and you are applying the same force, extension of copper will be less because it is higher compared to brass. Okay, so these are simple stuff, right? But I'm giving you these as theories because you will need these when you are doing questions, right? You will see that. Okay, so I have given you like all the fundamental equations. Now we have to do some questions, right? Write this question on the theory note, not on the not on the other papers, right? Write this on the theory note itself, this question. Quickly we'll write that. Write down a Q, put a Q there. Write down, when a copper wire when a copper wire when a copper wire with cross-sectional radius when a copper wire with cross-sectional radius 2 millimeter, cross-sectional radius 2 millimeter, comma, length 40 centimeters, length 40 centimeters, length 40 centimeters is applied a force of 2000 Newton, a force of 2000 Newton, force of 2000 Newton. Calculate the extension of wire. Calculate the extension of wire calculate the extension of wire. Okay, you can try this. For the copper, the data is given initially in the note, right? You can use those. You can try. Just first write the equation. This is the equation. So what they ask is extension. So first subject extension, then do the substitution. So FL over AY. Cross multiply and then get this equation. Once you get this, just substitute, right? Substitute and get the answer. Still these are like the basic, right? Basics. Substitute the values and get the answer. You have to do the simplification, right? You will have similar simplifications in the exam, so you have to practice for these simplifications, right? Force is 2000. Length is 40 centimeters, so it is 0.4 meters. You have to substitute it in meters. So this is the Young's modulus, and the radius also should be substituted in meters, right? So this is cross-sectional area, so that is a circular, right? This is a wire, so it is cross-section is circular. So you have to use phi r squared. Phi r squared. Phi radius is 2 millimeters. 2 millimeter squared. Millimeter squared convert into meter squared, it becomes 10 to the power minus 6. Minus 6. Okay? I think you understand that. Millimeter squared. Millimeter is 10 to the power minus 3 meters. So square of that 10 to the power minus 6 meters squared. Okay? Take this to be 22 over 7. 22 over 7. You have to do the simplification, right? Okay, if you did the simplification, send me a message, right? You have to practice these simplifications. Once you did the simplification, send me a message. So this is 22 over 7. 7 goes up. 22, this is 22 over 7. 7 goes up. Yeah, the answer is okay, 0.53 millimeters. 0.53 millimeters. Okay, so that is the extension. Okay. Right, 0.53 millimeters. Okay, then write the topic. So this is a key main. This is one of the key part of this lesson. Write the topic: stress strain curve. Stress strain curve. This is a topic: stress strain curve. Or we can call that sigma epsilon curve. Sigma epsilon curve. Right. Write down the stress strain curve. The stress strain curve for a metal wire. Stress strain curve for a metal wire submitted to tension, submitted to tension by hanging a load, is shown below. By hanging a load is shown below. Okay. So this is the stress strain curve, right? So this is defined for a material. So this axis we have stress F divided by A, and this axis we have strain E divided by L. Stress and this strain. So what we do is, so this is a rod. So let's say you are applying a tensile force. You are applying a tensile force. Then this extends, right? As you increase the force, think about it like a spring. When you increase the force, simple E increases. So when you increase this one, E increases proportionally like this. So this is a linear. Initially it is linear like this. So this is linear. Up to a certain point. So this could be made of any material. So this is linear. Up to a certain point, this is linear means these two are proportional, right? Then what happens? Let's say you are further increasing this one, further you are applying the force. Then what happens is that linearity goes away and it tends to be like this, right? Then it goes to B. B we call that elastic limit. A we call that proportional limit. This is proportionate limit. And this B we call that elastic limit. Elastic limit means when you remove the force, it will follow the same path and comes to the original shape. It will take the original shape. So that's what elasticity means. When you remove the force, it will gain the initial shape, original shape. So that's what happens here. Up to here, you can apply forces on that rod or wire. When you release the force, it will follow the same graph and comes to this here. Okay. So we call this elastic limit. This is proportional limit because proportionality stops from here. After that, this is called elastic limit. Okay. Then there's another point called yield point. Yield point means when you further apply stress, it extends. So this is called yield point. And if you further keep increasing the force, it gets a shape like this and comes to a point called C dash. Then you further keeps increasing the force. Here, this point is called breaking point. Sorry, this is the maximum stress. This is the maximum stress that material or the rod can bear. So this is the maximum stress. And at this here, this rod breaks. So we call this capital E breaking point. Capital E is called breaking point. Okay. So you might have seen when you keep increasing the force on a metal rod, the cross section decreases, then it breaks. Cross section decreases, then it breaks, right? So this breaking happens at E. The maximum, once you provide this rod, the maximum stress, this breaks. Once you provide the maximum stress, this breaks. Okay? Right. So another point is, let's say you have, you are here. Now the elastic limit, B is the elastic limit. You have passed the elastic limit and you are here. And when you remove the force, what happens is, it doesn't follow the same graph. It follows a path like this. When you remove the force, it follows a path like this. Let's say you remove the force here, it follows this path and comes to P. Okay. First, just take this down. First, take this graph down. Clearly mention all the points. Clearly mention all the points. If you did draw the graph, send me a thumbs up. In the exam, they ask these points, right? What are these points? They ask. What is A, what is B? Those are. Right. I think you had drawn the graph. Then you have to name these points. So point A, name it as proportional limit. Take it down. Proportional limit. Point A is proportional limit. Then point B, we call that elastic limit. Point A, proportional limit. B, elastic limit. C, we call this yield point. Yield point. C is yield point. Then capital D is break-in stress. Break-in stress means when you provide that stress, it breaks, right? When you go here, it is a maximum stress. So D is break-in stress. Then E is here. It is where that breaks, so it is called breaking point. It is called breaking point. That is capital E. Capital E is breaking point. Okay. Capital E is breaking point. Right. Then below this, write down since the graph is linear, since the graph is linear, since the graph is linear from O to A, graph is linear from O to A, O to A, up to capital A, up to capital A, up to capital A, up to here. So what happens? This is the strain, this is the this is the strain, this is the stress. So what happens here is this is proportional to stress only up to A. Take this down. F over A proportional to E over L. F over A proportional to E over L. Take it down. Then you can write this one. F over A is equal to Y E over L. You can put a constant there and write this down. Okay. So what does this mean? When you have materials, this equation is only applicable. This equation is only applicable up to A. It is only applicable up to A, right? So that is what it means. Okay. So after that, it is not proportional. So we cannot use this equation after this, right? So it is only up to A. Then we can think according to this graph, this is the y-axis and this is the x-axis, right? So we can say stress is y, strain is x. Then Young's modulus should be the gradient, right? So this is a y equals mx graph. Y equals mx graph. Okay, take this down. So y is f over a, x is e over l, and the gradient should be capital Y. So it follows a y equals mx graph up to O, from O to A. Take it down. So that is y equals mx. So according to that, gradient, what is the gradient? Gradient of this graph is capital Y, right? So gradient of this graph is capital Y. So that is the Young's modulus. That is the gradient. Write this down. Gradient is capital Y. Gradient is capital Y. So I talked up to A. So only up to A you can apply that equation, because only up to A it is proportional, right? Okay, below this, right? So what I'm doing is explaining this graph, right? So as I'm explaining this, understand. Okay, write down. From A to B, this one, from A to B, strain is not proportional to stress. Strain is not proportional to stress. So you can see it is not proportional, right? This is curved. So it is not proportional. Then write, but if stress is lowered, gradually from O to B, strain decreases, following the graph. Strain decreases following the graph. Then write, when the load is fully removed, wire regains its original length. Wire regains its original length. Okay. So what they say is when you release the force somewhere here, it follows the same graph and comes to zero. And again it has this initial length, because once you remove the force, strains becomes zero. There's no extension, right? Extension of the wire, so it becomes zero. It doesn't have a permanent change. Okay, now from A to B we described that. Then write another point. From B to C, from B to C, from B to C, each molecular layers starts sliding. So what happens from B to C? Now the proportional elastic limit as well is, now it is beyond the elastic limit. So what happens is, so these are made of molecules. These starts to slide over each other. That happens within B to C. So this region, you can see this is elastic region. When those layers start to slide, that means this should be the plastic. So this is going to show plastic properties after this, right? Write down. This is called plastic flow. This is called plastic flow. Plastic flow. Then write to the same sentence, to the same line. C is the yield point. C is the yield point. C is the yield point. Beyond that, graph is in plastic region. Graph is in plastic region. Here, for a small increase of stress, strain increases largely. So there's a small increase of stress. Strain has increased largely. To the same line, right? In a point like C dash, if stress is gradually decreased, strain of wire changes, strain of wire changes not along initial graph, not along initial graph, but along a line like C dash P, a line like this is C dash P, C dash P. Then even the load is fully removed, then even the load is fully removed, a permanent strain, a permanent strain OP, this is P, permanent stress OP causes, a permanent stress OP causes. Okay, so explain from B to C dash, B to C dash. So what happens when you release the force from here? It doesn't follow this graph. It follows C dash P. Follows when you release that, it follows C dash P. Okay, follows C dash D. Right. Then we have to talk about from C dash to D. From C dash to D. Okay, from the next new rule, write down when the graph goes beyond C dash, goes beyond C dash, stress of wire increases, stress of wire increases up to D, and then the wire becomes thin, and breaks at E. Wire becomes thin and breaks at E. Okay, now what happens? The wire becomes thin and breaks at E. Okay, that's why the graph stops here. Right. Okay, then write down from a new rule, materials that follows this graph, materials that follows this graph are called ductile materials. Materials that follow this graph are called ductile, right? Ductile. Meaning that those materials can stand, it doesn't break. Even when you are applying force, keep applying the force, the material does not break, right? It breaks somewhere here, but it keeps extending. So that's what ductile means, okay? So write this example for ductile materials. Copper, steel. So mainly many metals are ductile materials. Copper, steel. Okay, from a new line, right? Materials that breaks right after elastic limit, are called brittle, brittle materials, are called brittle materials. Okay, so some materials, what happens? They can't follow this graph like this. They doesn't keep extending, right? So for those materials, the graph only is up to here, up to the elastic limit. It's only up to the elastic limit. So those materials are called brittle materials. Right. Then we'll write some examples for brittle materials. Write down examples. So we know that glass is brittle. It easily breaks, right? Doesn't keep changing the thickness. Glass is a brittle material. And there's another material called cast iron. Write down glass and cast iron. Okay, so now I have explained the whole graph. In the exam they ask these points, right? So you have to clearly understand each points of this graph. In the exam they ask those points, okay? So you have to remember that. So for ductile materials, follow these graphs like this up to somewhere here. But for brittle materials, it breaks once it passes elastic limit. Right. Okay. So those are the basics. So then we need some important points before moving to doing questions. Put a star mark, and write down stresses. Write down stresses at proportional limit. Stresses at proportional limit, comma, elastic limit, and break-in stress, are constant for a specific material, okay? So you have to remember that. So this is what we call. So here we have the proportional limit. Then there's the elastic limit. And then there's breaking stress. So this is the break-in stress. So these are constants for materials. Like when we have iron, it follows these types of a graph. If we have copper, it could follow a graph like this. Copper. So this is iron. But for anything made of that material follows the same graph. So each of these graphs are specified for the material. Each of these graphs are specified for the material. Okay? For the material. So that's what it means. So the proportional limits, yield points, and the break-in stress, those are specified for the material. Specified for the material. Okay? Then you don't have to draw this one. Then put another star mark. Another star mark. Write down. If a wire is not to be broken, if a wire is not to be broken when extending, if a wire is not to be broken when extending, F over A, write this one, comma, write this one, F over A is less than break-in stress. So we know that this is the maximum stress that the wire can withstand. So if the wire is not to be broken, so the stress we are applying to the wire should be less or equal to the break-in stress. So it makes sense, right? So from this equation I can cross multiply. I can put A here. Break-in stress times A. Okay. So according to this one, maximum force that can be applied without breaking the wire is equal to break-in stress times capital A. So maximum force that can be applied without breaking the wire is equal to maximum force that can be applied is break-in stress multiplied by capital A. So this is the maximum force that can be applied. Right, take it down, take it down. Then write down below that, right? Draw margin to that, okay? Draw margin to that. Below that, right? Therefore, maximum force a wire can withstand without breaking is equal to F max. This one is equal to F max. So these notes you will need this when we are discussing questions, right? Then write below that, right? According to this, F max depends only on the material and cross-sectional area. According to this, F max depends on only on the material and cross-sectional area. Length does not affect. length does not affect. Okay, so what it means? So we know that break-in stress is specified for the material, type of material. Break-in stress changes only when material changes, right? So that is break-in stress times cross-sectional area. So those two decides the maximum force that can be applied to the rod or the wire so it won't break without breaking the wire, right? So if we apply this force, so what it matters is what that rod is made of and the cross section. Remember that length does not matter. Length does not define when this is going to break. The force required for breaking this does not matter. Length does not affect that. Only cross section and the type of material are the two properties that decide when the rod is going to break under a force. Okay, so those are the two factors there, right? So I think up to there the note is complete, right? We'll do a question. Write down Q, write Q, capital Q. Find the maximum force. Find the maximum force. Find the maximum force bearable, maximum force bearable by a wire, bearable by a wire with 2 square centimeter cross section and made of a material with break-in stress 6 times 10 to the power 8 newtons per square meter. This is break-in stress. Yeah. Okay. Just try that one. So here what they ask is maximum force that can be applied without breaking the wire, right? So you can use this equation F max equals break-in stress multiplied by area. Okay, so break-in stress is this one. 6 times 10 to the power 8 newtons per square meter. And cross section 2 square centimeters. When you convert square centimeters into square meters, it is -4, right? So this is 12 times 10 to the power 4. Put a 10 here, then this is 120, then there's 1,000 remaining. I can put a kilo there instead of 1,000. So this is 120 kilonewton. So you can apply 120 kilonewton force without breaking this wire. Okay, without breaking this wire, right? Okay, take it down. If you don't understand, just send me a message. Okay, then we'll move on to the next theory part. Force extension FE curves. Force extension curves. FE curves. Take it down. So with this one you are already familiar because you have learned this in earlier when you learn mechanics. Okay, when you are learning mechanics you have learned this. Right. First take this down. Force dash extension. Force dash extension. For a metal wire, force dash extension for a metal wire submitted to tension by hanging a load is shown below. Okay, so this is force and this is extension. So what do? We hang a weight from this wire. Okay. So what happens? This weight means force, right? So when we increase this force, what happens is this wire gets extended. Initially it has a proportional extension. Once the proportional limit is passed, it follows a graph like this. Okay. Draw this graph. And this is point A. Quickly draw the graph. Okay, write down. Since the graph is linear, from O to A. Write down O to A. So what happens if it is linear? If it is linear, we can say force is proportional to extension. If it is linear, force is proportional to extension, right? Force is proportional to extension. Write this one. Force is proportional to extension. Okay, you are familiar with this one. What is this called? What is this combination called? Force is proportional to extension. This is called Hooke's law, right? Hooke's law, remember that? Hooke's law. Force is proportional to extension. So that is Hooke's law. So below that, write this one. Up to proportional limit. Up to proportional limit. Up to proportional limit. Extension in a wire. Extension in a wire is proportional to, extension in a wire is proportional to the tension that it causes. The tension that it causes. Okay, then below that write, when you write this one, you can write F equals, you can put a constant there and put E here. So F equals KE. Then we can say this follows a Y equals mx graph. E is x. Then this should be the gradient, right? Take it down. This should be the gradient. Take it down. Then write gradient of OA equals K. Gradient of OA is equal to K. Gradient of OA is equal to K. So it is clear, right? Gradient is K. So within brackets in front of K, write K is the force constant of the wire. If it is a spring, it becomes a spring constant. But here it is a wire, right? So we call this one force constant. K is force constant of wire. Right, now we are going to learn a new equation for that force constant, right? Earlier you might have learned that when you break a spring in half, let's say the spring has a spring constant K, and if it is break in half and take a one spring part, the force constant doubles to that. Force constant doubles there, right? But once we discuss this part, you will understand why that is. Earlier you might not have learned that, why that is, right? Okay. I can relate these two equations. So this is the initial equation, F E over L. This is the initial equation. I can put this A here. So force is equal to YA E divided by L. Okay. Then I'm going to write this equation below here. F equals KE. So now what happens? If you compare these two, this quantity should be equal to K. So you can write K is proportional to YA divided by L. K is proportional to YA divided by L. Okay, take this down. Don't draw these. Take this down and write this. K is equal to YA divided by capital L. Therefore, K is equal to YA divided by capital L. Okay, right. Under this one, right? Wires made of the same material. Wires made of the same material, but different A comma L, capital A, capital L, can have different K values. Can have different K values. Okay. Got it? So what does this mean? Let's say you got two wires, right? Two wires made of the same material. Let's say copper. You have two materials made of copper. Meaning Young's modulus is same for both. Young's modulus is same for both. But if two materials have different dimensions, right? Different dimensions. If one, let's say like for example, one is lengthier. Even both has same Y because both are made of the same material, but the dimensions are different. Cross section also can change, right? Therefore, K changes even though Y is the same for both. Spring constant changes. K changes, right? Y depends only on the material. So since both wires are made of the same material, Y is the same. But since the dimensions are different, if dimensions are different, Y is still same, but K changes. You can see when you look at this equation, right? Right. Then below that, write down by changing dimensions of a wire, by changing the dimensions of a wire, simple K can be changed. Simple K can be changed. Example, when a wire is cut in half, when a wire is cut in half, that is example, right? When a wire is cut in half, K doubles. K doubles. Right? See that? Let's say the wire is cut in half. So this gets half. Then what happens to K? K doubles. if this wire is cut in half, because this is at the denominator, what happens? K doubles. Let's say these two are constants. Constant means the same wire. If you cut a wire, A does not change, material does not change. What changes is the length. Length halves. Then what happens to the spring constant? Spring constant doubles, right? Because length is at the denominator. Okay, right. So that is the combination between Young's modulus and spring constant, right? So the key point of this is Young's modulus only dependent on the type of the material, But spring constant depend on the dimensions of the wire as well. Okay. So these stuff will be useful when you are doing questions. Okay. Okay. Then we are going to move on to the next topic. Right. So in the next topic, so we've been talking about wires and rods, single wires and rods, right? Then we have to talk about systems of wires and rods. So rods, those can be connected either in series or in parallel. So those types of systems we have to talk about. Right. Write the topic. First, I'll talk about wires in series. Write this one. Wires in series. Okay, first we'll take the note, then I'll explain. Write down. When a load is hanged by a system of wires in series, hanged by a system of wires in series, tension of each wire has the same tension equal to the load hanged. Okay, right. So here we are talking about first I'll just talk about just two wires, right? So let's say this is one of the wire, then we have the another wire. So these are connected in series, then you just hang the W here. In this lesson we are only talking about light wires, right? Light means wires without any weight. So we know that whenever you have a light wire means a wire without any mass, tension of that wire is same, meaning the tension of the wire at this here is equal to the tension everywhere here. So everywhere the tension is just W, right? These are two types of wires, but since those wires are in series, what happens? Tension is the same, meaning the force is the same throughout the compound wire. Tension is the same. Okay, right. Then the next point, write down. total extension of system is the sum of extensions of each wire, okay. That's the another point for wires in series. Here what happens? Now the tensions are the same for both. These can be made of different wires and have different lengths, different cross sections. But the tension is the same if the wires are connected in series, right? Tension is the same. So in the next point, what they say is, let's say this gets an extension E1 and this gets an extension E2. So if you think about the whole wire, what's the extension? E1 plus E2, okay? For the whole wire, extension should be E1 plus E2. So that is really obvious, right? So what are the two things you have to remember when the wires are in series? Throughout the wire, through the wire, everywhere, the tension is the same. Another one is extensions of each wire. Sum of extensions of each wire is equal to the total extension of the wire. So the total extension should be E1 plus E2, right? So those are the two key points that you have to remember. Actually, you don't have to remember, it is obvious, right? Whenever the wires are in series, those two properties stands out, right? Okay, I'll just explain this theory part from a question, okay? From a question. Write down. Actually put Q1 here, right? I'm going to give you two questions from this part. Q1. A steel wire write down. A steel wire and a copper wire. A steel wire and a copper wire with same length 40 centimeter has cross section of 5 square millimeters. And they are connected in series. When a load is applied, total extension of the compound wire is 6 millimeters. Find the load applied. First, if you want to draw a sketch, you can draw a sketch. So, steel wire and we have the copper wire. 5 square millimeter, 5 square millimeter, 40 centimeter, 40 centimeter, and each wire extends by E1 and E2. Then the 6 millimeter is the sum of those extensions. Okay, just try this one. I'll give you a minute. Try this. Right? Okay. So from that equation we can get this one, FL over AY, right? You can derive that equation. You can have this one. Then you can apply this to each wire. Then another equation is total extension is equal to extension of each wire. E1 plus C2. E1 plus C2. Each wire extension is equal to E. Then you can use that equation. Okay, I'll just apply that. E is the total wire, right? We know that for the compound wire, for the whole wire, the extension is the same. So I'll just put F here. No. So we know that E1 plus E2, that is E. For this wire, I'll put F. So everywhere the load is the same, right? Let's say this load is the same, F. So if I apply that to here, it also has a tension F. This also has the same tension since they are in series. So the equation is FL divided by AY. F length is 40 centimeters, 0.4. Then we have cross section, and cross section is 5 square millimeters. Square millimeters means when you convert into square meters, 10 to the power minus 6. Then you have the Young's modulus. Young's modulus is for steel. Earlier you have that data, right? That is 2 times 10 to the power 11. You can use that data in the note. In the exam they give those values, right? You don't have to remember. Okay, so this is for the steel. Then for the copper, same force. Length is 40 centimeters, 0.4 meters. Cross section is same, right? 5 minus 6 converting to meter squared. Young's modulus is, for copper, Young's modulus is 1.2, 10 to the power 11. Okay, so this also is somewhat covered. Then this whole thing is equal to E. E is the sum of total extension. So that is 6 millimeters, 6 times 10 to the power minus 3. So everything should be written in meters, right? So 6 times 10 to the power minus 3. Then you just have to simplify this one. Okay. Don't be lazy to simplify this stuff. They will ask this in the exam, right? Okay. Simplify this and get a value for f. So that's what you have to do. This is not hard to simplify. This is, you can take same values out. Okay, quickly tell me the value. Now you have to simplify it. Might take some time, but don't be lazy when you are doing simplifications, right? Okay, get a value for that term, right? Get a value for capital F. Check whether that value is somewhat 16,875 Newton. 16,875 Newtons. Okay, then the next question, do the simplification if you hadn't done that yet, right? Question 2, a wire, a wire is made of a material, is made of a material with break-in stress, with break-in stress 6 times 10 to the power 8. 6 times 10 to the power 8 full stop. Another wire, another wire is made of a material is made of a material with break-in stress with break-in stress 4 times 10 to the power 8. These are the values for each wires. And cross section of each wire is 5 square millimeters. Each wire is 5 square millimeters. Then if the wires are connected in series, to make a wire compound, find the maximum stress that the wire can withstand. Maximum stress that the wire can withstand. Right? So if you notice in the question, they haven't given length of wires. Okay? Don't we need the length? We don't need the length. If you remember the previous theory part, the break-in of wires only dependent on the material the wire made of and the cross-sectional area of the wire. So let's say this is wire 1 and wire 2. Wire 1 and another wire 2. So what I'm going to do is I'm going to find F max here for this wire and F max to this wire. Then you can decide, if you think about the compound wire, then you can decide what's the maximum stress that this wire can withstand. So first I have to calculate F max values. So I'll calculate F max 1 for the first wire. So that is sigma break-in stress times cross section. So for the first wire it is 6 times 10 to the power 8. Cross section is given 5 square millimeters. 5 minus 6. So this is 30 times 10 to the power 2. So we found 3000 Newton. What does this mean? The maximum stress, is it correct? 6 times okay, 3000 Newton. Then I am going to find this for another one. Another wire, that is this one. 4 times 10 to the power 8. Cross section is the same. So it is 5 times 10 to the power minus 6. 20 10 to the power 2. This is 2000. So what does this mean? The maximum stress second wire can withstand is 2000 Newton. And this wire can stand at 3000 Newton. So what about the maximum load that you can apply here without breaking this compound? Okay. So if you think about that, this should be 2000, right? Should be 2000. Why? So this is 2000 Newton. Because when we apply 2000 Newton. This wire won't break. This wire either does not break because this wire can withstand 3000. But if we apply like 2500 Newton, this wire breaks, meaning the maximum stress that the maximum force that this wire can withstand is 2000 Newton. That is 2000 Newton. Okay. Yeah. So I think now you understand wires in series. Then I have to talk about wires in parallel, and I'll do a couple of questions on that. So these will be done on the next week, right? I have to further talk about the theories on wire systems that are parallel wire systems, and elastic potential energy, other one elastic potential energy, and the effect of heat. Those are not that big parts. I probably can finish within like an half an hour. After finishing that, I'll be discussing the questions on the tute. Okay, right. Then okay. Then we'll meet on the next class on the next week, right? Okay. Good night, everyone. Okay.